Modern science operates in isolated silos. We use one set of equations to calculate the momentum of a falling object, another to measure the energy of a photon, and entirely different math to determine the bandwidth of a wireless network. Independent researcher Fadi Ghali argues that these boundaries are artificial. His white paper outlines a unified architecture called the GULF law. Looking at the core equation, this framework distills all realized phenomena, which he labels R, into the mathematical product of exactly two variables. The text asserts that this single operator reproduces outcomes of quantum mechanics, of macroscopic gravity, of biological rhythms, and digital data transmission. If validated, physical reality and digital emergence are no longer governed by disparate forces. They become deterministic outputs of a single universal frequency context operator. The first variable is the Fadi Tempo Unit, TF, an independent, indivisible quantum of rhythm, a repeating tick. Researchers calibrate TF to the system's smallest measurable period, whether the firing interval of a neuron or the cycle time of a microprocessor. The second variable is the quantum context, or QC. This multivariable operator replaces a static constant, encapsulating every relevant state acting on the system, from quantum probabilities to thermodynamic temperature and local field strengths. By structuring reality this way, the framework shifts the burden of discovery. The challenge becomes correctly modeling the parameters within the quantum context array to output an accurate result. The Gulf law operates as a computational engine designed for direct simulation rather than theoretical physics alone. Looking at the explicit Python logic, a specific loop multiplies the baseline rhythm against environmental factors. The system initializes the base period at 1 millisecond, injects numerical values for the target's physical states, and outputs R, the computable resolution. This coding structure forces physical or digital events to be defined by measurable variables in software. To test this architecture, the framework must map directly over the established laws of physics, starting at the subatomic level. Max Planck formalized our initial understanding of quantum energy. Looking at his equation, energy equals Planck's constant times frequency. The derivation begins by inverting the standard frequency variable into the Gulf period. To keep the math balanced, the quantum context array transforms into Planck's constant times frequency squared. Under this substitution, energy becomes a secondary scaling factor, strictly dictated by its underlying frequency. The model then scales its operator from subatomic particles to macroscopic astrophysics. General relativity relies on the geometric curvature of spacetime to explain mass and gravity. The text tests its alternative mapping against exact empirical data collected from binary black hole mergers at the LIGO facility. Looking at this simulated waveform, the framework uses Fourier analysis to extract the dominant frequency, isolating the minimum period as the TF variable. The quantum context array then populates with the remaining data, the mass, spin states, and topographical grid. The predictive output must perfectly reconstruct the observed waveform from LIGO data. This math replaces the geometric fabric of spacetime with a localized frequency calculation. The framework pushes this logic into digital architecture, crossing from physical mass to data transmission. Claude Shannon established the foundational limits of signal processing. Looking at this network visualization of the channel capacity equation, we see the limit for transmitting information over a noisy channel. The mapping converts Shannon's bandwidth variable into a symbol period. The remaining elements are absorbed into the quantum context array. Through the Codex Transform, the equations governing quantum energy, gravitational waves, and digital networks are abstracted into identical, generalized information processing logic. Mathematical claims require strict testing parameters. The text embeds explicit Popperian falsifiability protocols directly into its architecture. The author challenges researchers to test the mathematical operator across three distinct empirical domains: LIGO gravitational waveforms, ECG cardiac rhythms, and the kinematics of drone swarms. The failure conditions are direct. If the framework's calculated prediction does not match the empirical observation, the law fails. Any outcome that falls outside the standard margin of experimental error instantly invalidates the framework for that specific domain. This reliance on falsifiable data separates the text from purely philosophical theory. It provides researchers with a globally testable what-if simulation engine. The author is currently applying this mathematical foundation to real-world engineering, specifically the governance of artificial intelligence. Using a model called persona as a software, the engineering goal is to constrain the stochastic, highly variable nature of modern text generators by mapping cognitive states as explicit frequency variables. The objective is to take chaotic, unconstrained AI emergence and force it into a strictly governed rhythmic output based entirely on the Gulf equation. Whether this mathematics proves to be a structural breakthrough or an esoteric repackaging of established physics, its formal architecture invites rigorous empirical scrutiny. Ultimately, the Gulf framework challenges engineers to abandon isolated physical models. It demands that all natural phenomena and digital systems be treated strictly as computable, deterministic states of frequency and context.